In this lesson, we're going to cover integration of rational functions by partial fraction decomposition, u-substitution, completing the square, and also tan inverse of x. First, we have an irreducible quadratic factor in the denominator, where your discriminant, b squared minus 4ac, is negative. Then you'll use u-substitution and integrate, or you'll complete the square and integrate using the following formula. So we have the formula, the integral of 1 over x squared plus a squared, and it equals 1 over a tan inverse x over a. So here I created a flowchart to kind of walk you through which type of problem it's going to be. When you have a proper rational function, first you're going to check whether the denominator does not factor or whether it factors. Once you identify that, if the denominator does not factor, you're then going to check the numerator. Either the numerator is going to be a constant or it's going to have a variable in it. If the numerator has a constant, you're going to complete the square of the denominator, and then you'll be able to rewrite the integral so it's of this form, and then finally you can use the formula 1 over a tan inverse x over a to integrate. If the numerator has a variable, you're going to let u equal the denominator, and then I call it getting creative, and you're going to split the numerator up and then integrate the following fractions. If the denominator factors, then you'll do partial fraction decomposition, and then you can consider each part of the problem. Either you'll let u equal the denominator, then you'll have something of the form the integral of 1 over u, which is ln absolute value of u, or you'll have something of the form 1 over x squared plus a squared, where you can again use the formula 1 over a tan inverse x over a. This example says the integral of, and we have dx over 4x squared plus 4x plus 7. So if you check the denominator, it doesn't factor. So I just wrote that denominator does not factor. Next, we check the numerator. The numerator is a constant. Technically, it's the value 1. So I wrote numerator is a constant. So again, I want to look at the flowchart. We have a proper rational function. Denominator does not factor. Numerator is a constant, so we're going to complete the square of the denominator. And again, I have that written out here. So whenever you complete the square, your x squared term needs to have a coefficient of 1. So what we're going to do is we're going to factor out this 4. So when you factor out 4, you're left with just x squared. And we're also going to factor out 4 from this term right here. So we're left with 2x. Then I left a little blank here. And then this constant 7, I'm going to move it to the side. And then finally, I left one more blank right here. I'll explain that in just a second. When we complete the square, we take the b term right here, and we divide by 2. So 2 divided by 2 is 1. And that's what we're going to add right here. So we put a 1 right here, but it's inside of a parentheses being multiplied by 4. So it's actually a value of 4 that's being brought into the problem. To keep this entire expression equivalent to this one, if we're adding in 4 here, we're going to put minus 4 over here. So mathematically, this entire expression is still equivalent to this one. Because again, if you distribute this 4 in, you would get 4x squared, so that's fine. You'd get 8x right here, that's good. Then you get a positive 4. Plus 7 minus 4. So the positive 4 and the minus 4 cancel out, and then you just have the plus 7. So again, I just want to show that these are mathematically equivalent. For our next step, we're going to take this 4 and distribute it back in. So when you distribute the 4 in, you get this trinomial right here. And then over here, we're going to combine these two constant values, so they become 3. Now if we take this trinomial and we were to factor it, it becomes 2x plus 2 quantity squared. Because 2x times 2x is 4x squared. 2 times 2 is 4, and then when we do our outer and inner, it's 4x and 4x, which combines to 8x. For this 3 right here, we want it to be something squared, but because this isn't a perfect square, we're going to use the square root of 3. So now we have something squared plus something squared. So we're going to take this whole expression and plug it in right here. So now we have the integral of 1 over 2x plus 2 squared plus the square root of 3 squared dx. So it might be a little bit hard to recognize, but if you look at this expression and we go over here to this formula, if you have the integral of anything of the form 1 over something squared plus a constant squared, you can use this formula to integrate 1 over a tan inverse x over a, where whatever's being squared here goes here, and the constant that's being squared here goes 1 over a and then x over that value. So when we look at this integral, we have 1 over something squared plus a constant squared. So this is of the right form to use our tan inverse formula. But because when we're integrating, this isn't just plain x, we're going to use u-substitution. So we're going to let u equal this 2x plus 2. Next, we're going to take the derivative with respect to x. So the derivative of u with respect to x is 1, and then we times by du dx. Over here, the derivative is just going to be 2. And then we're going to rewrite this. It's a proportion, so we can cross multiply. We're going to bring this dx up, and we're going to bring the 2 down. So we get dx equals du over 2. So we're ready to plug all of this in over here. So we have the integral of 1 over u squared plus the square root of 3 squared times du over 2. I'm going to pull this 2 to the front as a 1/2. And now this integral is of the form 1 over something squared plus a constant squared. So to integrate this, again, we're using the formula 1 over a tan inverse x over a. So I dropped the 1/2 down, and now to use the formula, we're going to go 1 over a, where a is the square root of 3. So we have 1 over a, and then tan inverse x over a, where in this case, x is u. So we write u over root 3. We're almost done. At this point, we're just going to plug our u back in right here. So our final answer is 1 over 2 root 3 tan inverse of 2x plus 2 over root 3 plus c. Our next example says the integral of, and we have this rational function. Again, this is proper where the degree of the numerator is less than the degree of the denominator, so I wrote that here. The next thing we want to check is whether or not the denominator factors, and this denominator does, so I noted that the denominator factors. So then, according to the flow chart on the front side of the notes, we're going to use partial fraction decomposition. So our first step for partial fraction decomposition is we factor the denominator, so you get x times the quantity x squared plus 3. So we take this first factor of x and we put it in the denominator of the first fraction. This is a linear denominator, so our numerator is going to be a constant. So I'll use the letter a. Next, we take this factor and we write it as the denominator of our second fraction. So you get x squared plus 3. This denominator is an irreducible quadratic, and since it doesn't factor anymore, hence irreducible, we're going to use a linear numerator. So we'll go down in the alphabet, so we'll start with b, x, plus c. So now we have our fractions set up. Next step is we're going to multiply both sides of this equation with this expression. When we multiply this side of the equation with this expression x times the quantity x squared plus 3, the entire denominator gets canceled out with that. So all you have left is just the numerator. Over here, we're going to distribute this to both terms. So when we multiply this fraction by this expression, the x's are going to cancel, so all that's left is a times this quantity. Next, when we multiply this expression to this fraction, this x squared plus 3 is going to cancel, so we're left with bx plus c times x. Okay, our next step is we're going to distribute this a and we're going to distribute this x. Now we're going to group our terms. We have x squared here and an x squared term here, so we're going to move them together, and I'm going to factor out the x squared. Next, we're going to bring down this term with x in it, and finally, we're going to bring down the term 3a. Now we're going to look at the individual terms on each side. On this side, we have 1x squared. Again, its coefficient is a positive 1. And over here for x squared, its coefficient is the quantity a plus b. So we're going to set 1 equal to the quantity a plus b. Next, we're going to look at the x terms. We have negative x, and over here we have cx. So we're going to take the coefficient of the x term here and set it equal to the coefficient of the x term over here. So we're going to set negative 1 equal to c. And finally, we're going to take this constant and set it equal to this constant. So we can take these equations and solve for a, b, and we already have c. So first we have that a is equal to 2, and then we're going to take 2 for a and plug it in right here. So we end up getting that b is equal to negative 1. So now we have a, b, and c. We're going to take all of them and plug them into here and set up our integral. So again, a is 2, so we're going to plug that in here, so we get 2 over x. b is negative 1, and c is negative 1. So we're going to plug them in right here and put it over x squared plus 3. Looking at this integral now, we can integrate 2 over x. You would drop the 2 down, and then the integral of 1 over x is ln absolute value of x. Over here, though, we have a little bit more going on. First thing I would do is I'd look at the denominator and go, okay, if I let u equal the denominator, what's the derivative? You would get 2x, and that isn't going to really quickly cancel out with this entire numerator. So what we're going to do is we're going to take this fraction and we're going to split up the numerator. So we go negative x over this denominator. So we have negative and then x over x squared plus 3. And then we also have negative 1 over the same denominator. Again, when you have multiple terms in the numerator, you can split the fraction up to multiple fractions. So by splitting this fraction up to 2 different fractions, we can then split up this entire integral to 3 separate integrals. So we're going to do this one, like I already mentioned, with the ln absolute value of x. Right here, we're going to use u-substitution, and we're going to let u equal that entire denominator, so I'll show that work over here. And then finally, this is actually of the form 1 over x squared plus a constant squared, so we can use the formula 1 over a tan inverse x over a to integrate this last one. So first I want to work on this middle fraction. I'm going to let u equal the denominator x squared plus 3. So when we take the derivative, we get du dx equals 2x. And then we can rewrite it as dx equals du divided by 2x. Let's go ahead and plug this in right here. And again, for our last integral, I'm going to rewrite this as x squared plus the square root of 3 squared. All right, so right here for this middle one, I'm going to cancel these x's, and then I'm going to pull this 2 to the front. I'm going to pull this 2 to the front as a 1/2, and we're ready to integrate. So for this first one, we get 2 ln absolute value of x. Next, we get negative 1/2 ln absolute value of u. And for this last one, remember the formula is 1 over a tan inverse x over a. And in this case, a is root 3. And last step, I'm going to plug this u back in from over here. So here's our final answer, and then instead of absolute value, because this will always be positive, you can rewrite it as ln of parentheses x squared plus 3. But again, either of these is totally fine, and that's your final answer. For this example, we have the integral of this rational function. It's a proper rational function because the degree of the numerator is less than the degree of the denominator. Next, we want to check the denominator. The denominator does not factor. So then, according to the flow chart, we're going to check the numerator. And the numerator is a variable. So what we're going to do, according to the flow chart, is we're going to let u equal the entire denominator. So next, we're going to take the derivative with respect to x. So we get du dx equals 2x plus 2. And we're going to rewrite this proportion. So we get dx equals du over 2x plus 2. And then I'm going to factor out a 2 here. Okay, so at this point, we have this denominator. It's 2 times the quantity x plus 1. If this numerator was x plus 1, this would be a pretty traditional u-substitution problem. But since it's not, what we're going to do, according to the flow chart, is we're going to get a little creative. We're going to split this numerator up so that we can use this x plus 1. So we're going to take this 4 and we're going to break it up so that we have a value of 1. And to do that, we're going to go 1 plus 3. So again, this is really different than anything we've ever done before. We're taking the expression x plus 4 and we're breaking it up to x plus 1 plus 3. And again, this 1 is because of this 1 right here, and then 1 plus 3 makes 4. So now what we're going to do is we're going to split this fraction up. So we take this x plus 1 and we made it x plus 1 over the denominator, and then we take this 3 and we broke it up to 3 over the same denominator. Again, we just took this fraction and split it to 2 separate fractions, and then we take the integral of each individual fraction. So now at this point, we can use this work to evaluate this integral over here. I'm going to take all of this and plug it in over here. We're letting u equal the denominator, so we're just going to write u right here. You can see I left the numerator as just x plus 1. This is going to be the rigged part of the problem. And then this dx, we're going to use this expression over here. So we're going to replace it with du over the quantity 2 times x plus 1. And again, now this is just a traditional u-substitution problem. The rigged part of the problem is going to cancel with the derivative over here, so that works out great. And then we're going to pull this 2 to the front as a 1/2. So we're just left with the integral of 1 over u du. Then we have this side of the problem. It's a proper rational function. The denominator does not factor, but the numerator is a constant. And when that's the case, according to the flow chart, we're going to use completing the square. So we're going to complete the square on this denominator. When completing the square, the a value in front of the x squared needs to be a 1, and it is, so we're good there. And I dropped the 5 down right here, and then I left 2 blanks. So to complete the square, we're going to take this b term and we divide by 2. So 2 divided by 2 is 1, and that's what we add right here. This 1 isn't inside of a parentheses, so we don't have to multiply it to anything. But again, we're trying to make this entire expression equivalent to this one. So if this is a plus 1, we're going to put minus 1 over here. So again, this entire expression is mathematically equivalent to the original. Next, we're going to rewrite this as quantity squared. So again, if you factor it, you're going to get x plus 1 times x plus 1, and you can rewrite that as quantity squared. And then over here, we're going to combine these to get 4. And finally, we want something squared plus something squared, so I'm just going to rewrite this 4 as 2 squared. So now we can take this expression and plug it in right here. All right, so at this point, I'm going to bring this 3 to the front, and now this is of the form 1 over something squared plus a constant squared. So we can use the formula 1 over a tan inverse x over a to integrate it. And technically, we're supposed to let u equal this x plus 1, but when we take the derivative over on the side, you're just going to get 1, and it doesn't generate any extra values. So we can go ahead and use the formula to integrate this. So I integrated this right here. I dropped the 3 down, and right here when we integrate, the a value is 2. So the formula goes 1 over a tan inverse, and then it goes x over a. So our last step is we plug this u back in right here, and then I just rewrote this as 3 over 2. So here's your final answer. All right, guys, thanks so much for watching.